On September 23, 2024, 16 days after 3I Atlas disappeared behind the sun's glare, something changed. Deep inside the object, approximately 1.2 astronomical units from Earth, a radio signature appeared that hadn't existed before. Not a reflection, not solar interference. A coherent emission at 1612 MHz with a bandwidth of less than 3 kHz, narrow enough to rule out natural broadband noise, repeating every 11.4 hours with clock-like precision. The detection came from the Allen Telescope Array during what was supposed to be a routine sky survey. The signal lasted 47 minutes before fading below the noise floor. By the time follow-up observations could be scheduled, 3I Atlas had moved deeper into solar conjunction, unreachable for another 3 weeks. We're now inside a critical observation gap. Ground-based instruments can't see the object until mid-October. JWST's schedule is locked until November, and the Chinese space station Telescope, one of the few platforms with the aperture and positioning to observe near-solar targets, is undergoing calibration until late October. If the signal repeats, we won't know. If it evolves, we'll miss it. And if it stops entirely, we may never understand what turned on.
Dr. Sharma, look at this. It's not static.
This isn't the first anomaly.
I see it.
Over
Lock
the
it
summer,
down and run a confirmation
3I
sequence
Atlas
immediately.
exhibited trajectory corrections. A magnesium emission ratio seen in 1 out of 20,000 comets, transient spectral lines with no known atomic match, and radio silence during a coronal mass ejection, when every model predicted a bright interaction. Each anomaly taken alone has a natural explanation. Each one sits just inside the boundary of plausible, but together they form a pattern that suggests organization, timing, response. Before we go deeper, hit like, subscribe, and tell me where you're listening from, because this story is still unfolding, because the object is still out there, and because for the first time since Oumuamua, we're not just watching something pass through our solar system. We're watching something that might be watching back. This is not science fiction. This is September 2024, Chapter 1, September 23rd, the 1612 MHz anomaly. The detection came at 3:47 UTC, during the graveyard shift when most of the world sleeps and only the machines stay awake. The Allen Telescope Array, 42 radio dishes spread across the high desert of Northern California, was running its 7th night of automated sky surveys. The program was mundane: catalog radio sources, flag transients, build databases. No one expected to find anything unusual, certainly not from an object already cataloged, already understood, already explained. But at 03:47, the signal processing pipeline registered an event: narrow bandwidth, stable frequency, Doppler characteristics inconsistent with terrestrial interference. The frequency was 1612.
Look at how beautiful the universe is.
MHz. To most people,
So many
that
stars,
number
so
means
many
nothing.
possibilities
To
out there.
radio astronomers, it's immediately recognizable. It's one of the 4 ground state hyperfine transition frequencies of the hydroxyl radical, OH, a fragment of water that exists wherever hydrogen meets oxygen in the cold vacuum of space. It's the frequency of hydroxyl masers, those strange amplifiers of radio light that bloom in star-forming regions, in the expanding shells of dying stars, in the shocked gas where supernovae meet the interstellar medium. But 3I Atlas wasn't near any of those places. It was alone, 1.2 astronomical units from Earth, receding at 43 kilometers per second, deep in the empty space between planets where nothing should be amplifying anything. The bandwidth was the first thing that caught their attention. Natural radio emissions from space are messy. They spread across frequencies, smeared by thermal motion, by magnetic turbulence, by the chaotic processes. Nothing matched. The frequency was clean, protected by international radio astronomy allocations. And the Doppler shift was wrong for Earth-based sources. The signal was redshifted by exactly the amount you'd expect from an object receding at 43 kilometers per second. the amount you'd expect from 3I Atlas. The signal lasted 47 minutes. During that time, it maintained extraordinary stability. The frequency varied by less than 0.1 Hz, a stability of 1 part in 16 billion. Natural masers can achieve high-frequency stability when they're in steady-state conditions, when the pumping mechanism and the amplifying medium are in equilibrium. But 3I Atlas was not in steady state. It was tumbling, outgassing, bathed in the variable radiation of the sun's extended atmosphere. Every model predicted that any maser activity should be chaotic, flickering, broadened by the complex dynamics of the coma. This wasn't chaotic. This was controlled. At 4:34 UTC, the signal dropped below the detection threshold. Not gradually, as you'd expect from a source rotating out of view or fading as a maser region depleted its energy. Abruptly, as if something had been switched off, the operations log was timestamped. The raw data was archived. And then, because protocol demanded it, the detection was flagged for review and the automated survey moved on to the next patch of sky. It would be 17 hours before anyone looked at the data. When the email arrived, subject line, ATA detection, possible OH maser, unusual characteristics. It landed in 43 inboxes across 6 institutions. Most recipients skimmed it, noted it, filed it for later. 2 people opened the attached data files immediately. One of them was Dr. Elena Vasquez, a radio astronomer at the University of California, Berkeley, who had spent the last 6 years studying hydroxyl masers in the Milky Way. She pulled up the spectrogram, expecting to see the broad, messy emission typical of cometary OH. What she saw instead made her sit back from her monitor. The line was a spike, single-peaked, symmetric, beautiful. She ran the standard checks. Instrumental artifacts. None. Baseline subtraction errors. The pipeline had flagged clean. Radio frequency interference. The frequency allocation was protected, and the Doppler shift ruled out terrestrial sources unless someone had built a transmitter on a spacecraft moving at exactly 43 kilometers per second on exactly the same trajectory as 3I Atlas. She pulled the object's ephemeris from JPL horizons. 3I Atlas was at right ascension 14H32m, declination plus 12 degrees 18, currently behind the sun from Earth's perspective but marginally detectable during brief windows of solar elongation. The Allen array had caught it during one of those windows, a 6-hour period when the object rose just high enough above the horizon, just far enough from the sun's radio-bright disk to be observed. The timing was lucky, or convenient. She checked the photometric period. 11.4 hours. Every observation since June had confirmed it. 3I Atlas rotated with metronomic regularity, one of the most stable light curves ever recorded for a small body. If the radio emission was tied to the rotation, you'd expect it to repeat every 11.4 hours. The 47-minute duration was exactly 69% of that period, not round numbers, not obvious fractions. But when she calculated it precisely, 47 minutes divided by 11.4 hours, she got 0.686, close to 1/15th, close to the angle subtended by a 24-degree cone sweeping once per rotation. She pulled up the shape models from the summer observations, elongated, possibly tumbling in a complex rotation state. If there was a localized emission region on the surface, a vent, an active patch, it would be visible for a fraction of each rotation as the object spun. 47 minutes fit within the plausible range, but the signal's narrowness didn't fit, and the stability didn't fit, and the abrupt cutoff didn't fit. She wrote 3 sentences in her observation log. Detection confirmed. Natural explanation plausible but incomplete. Recommend immediate follow-up. Then she sent an alert to the International Astronomical Union's Central Bureau for Astronomical Telegrams, requesting priority observing time at every radio telescope with line of sight to 3I Atlas. The response came back within 6 hours. All major facilities were either pointed at other targets, undergoing maintenance, or blocked by solar conjunction. The earliest available slot was October 14th, 3 weeks away. By then, 3I Atlas would be 1.5 astronomical units from Earth, fainter by a factor of 1/6, and the signal, if it repeated, might already be below the detection threshold. 2 days later, a second detection was reported. FAST, the 500-meter aperture spherical telescope in Guizhou, China, had been conducting its own survey of interstellar objects. On September 25th, during a brief visibility window, FAST pointed toward 3I Atlas's predicted position and integrated for 90 minutes. The signal was marginal, barely 3 sigma above the noise. But it was there, a narrow emission line at 1612 MHz, Doppler shifted by the expected amount, lasting approximately 40 minutes before fading. The detection was not published. FAST's observing logs are not publicly accessible in real time, and the Chinese Academy of Sciences maintains strict protocols for vetting results before external release. But word travels in small scientific communities. An astronomer at the National Astronomical Observatories of China mentioned the observation in a private email to a colleague at Caltech. That colleague mentioned it to someone at Berkeley. Within a week, a dozen research groups knew that the signal had been detected twice. Twice was not coincidence. Twice was confirmation. The first models began circulating in late September. They were cautious, hedged with uncertainties, careful to frame the observations in natural terms. Stimulated emission from hydroxyl radicals in the coma, excited by solar ultraviolet radiation, amplified by the geometry of the outgassing flow. It was plausible. OH masers do occur naturally. The 1612 MHz line is one of the brightest, appearing in environments where water molecules are dissociated by starlight. But the models struggled with the details. Why so narrow? Why so stable? Why the abrupt cutoff? And why, during a coronal mass ejection in early August when the sun had blasted 3I Atlas with a surge of UV and X-rays, had there been no radio emission at all? The CME should have been ideal for stimulated emission, a flood of high-energy photons pumping the OH molecules into excited states, triggering a bright, transient maser flare. Every model predicted it. Every radio telescope that observed during that period detected nothing. 3I Atlas had been silent when it should have been screaming, and now it was emitting when models predicted only baseline thermal noise. Dr. Vasquez sat in her office, late at night, staring at the spectrogram. The line was a single bright spike against the darkness, narrow and sharp as a needle. She thought about the phrase that kept appearing in the group emails, carefully phrased, always qualified. Coherent emission. Coherent meant organized. Coherent meant non-random. Coherent meant that somewhere, somehow, a process was generating radio waves with a degree of order that natural chaos rarely achieved. She pulled up the light curve data from the summer. The 11 4-hour period, rock solid across 3 months. She overlaid the radio detection times. The 47-minute signal had occurred at rotational phase 0. 73, about 3/4 of the way through the object's spin cycle. If the signal repeated every 11 4 hours, the next emission should have occurred on September 23rd at 15:21 UTC. But by then, the sun had rotated into the line of sight. 3I Atlas was behind the solar radio glare, unreachable, invisible. If the signal repeated, no one could see it. If it evolved, no one would know. And if it stopped entirely, if whatever had turned on decided to turn off, they would miss it. She wrote one more line in her observation log: "We're flying blind." Then she sent an email with the subject line, 3I Atlas. Urgent request for out-of-cycle observing time. The reply came 3 days later. Request denied. Insufficient justification for priority override. Somewhere 1.2 astronomical units from Earth, 3I Atlas continued its journey, spinning, silent, carrying whatever had turned on, whatever had emitted 47 minutes of organized radio light, deeper into the gap where no telescope could see. This is not science fiction. This is late September 2024. Chapter 2, September 28th, Cassini's Enceladus Playbook. Sometimes the answers we need have already been written. We just haven't recognized the handwriting yet. In 2005, the Cassini spacecraft made a discovery that redefined what we thought was possible in the outer solar system. Enceladus, a small, icy moon of Saturn, barely 500 kilometers across, was geologically alive. Plumes of water vapor and ice crystals were erupting from cracks near its south pole, jetting into space at hundreds of meters per second, feeding Saturn's E-ring with a constant stream of fresh material. The discovery was unexpected. Enceladus was supposed to be dead. Small bodies lose their internal heat quickly. Within a few 100 million years, they should freeze solid, inert, and quiet. But Enceladus wasn't quiet. It was venting an ocean. The follow-up observations revealed something even more remarkable. The plumes contained organic molecules, salts, and silica grains, materials that could only come from liquid water in contact with a rocky core. Beneath the frozen surface, Enceladus harbored a global subsurface ocean, kept warm by tidal heating as Saturn's gravity needed the moon's interior. It was a masterclass in how to find hidden oceans. Look for plumes, analyze their composition, measure the magnetic field interactions, calculate the energy budget. When Dr. Amir Patel at NASA's Jet Propulsion Laboratory read the reports about 3I Atlas's radio emissions, he thought immediately of Enceladus. Not because the objects were similar, they weren't. Enceladus orbited Saturn, locked in a gravitational embrace that constantly flexed its interior and kept the ocean liquid. 3I Atlas was alone, unmoored, drifting through interstellar space with no tidal forces, no nearby planets, no obvious source of sustained heating. But both objects showed periodic emissions tied to rotation. Both exhibited unexpected ionization signatures, and both challenged the assumption that small, isolated bodies should be geologically dead. He pulled the spectroscopic data from the summer observations. The magnesium-to-iron ratio was still bothering him. In typical comets, magnesium and iron occur together because they're both products of silicate weathering. You see magnesium, you expect iron. The ratio is usually close to 1 varying by a factor of 2 or 3 depending on the parent body's composition. For 3I Atlas, the ratio was 300. 1. That wasn't weathering. That was differentiation. That was selective chemistry. That was the signature of materials that had been processed, either by intense heat that vaporized the iron, or by some mechanism that separated elements with precision. Planetary differentiation happens when bodies are large enough and hot enough for heavy elements to sink to the core, while lighter elements rise to the surface. Earth's core is iron and nickel. The mantle is magnesium-rich silicates. The crust is even lighter, aluminum, silicon, calcium. But 3I Atlas wasn't planetary-sized. It was perhaps a few kilometers across, maybe 10 at most. Objects that small don't differentiate. They don't have enough gravity, enough pressure, enough sustained heat, unless something inside them was generating that heat. Patel ran the numbers. To maintain internal differentiation, you need sustained temperatures above 1,200 Kelvin, hot enough to melt silicates, hot enough for dense metals to migrate downward. For a body the size of 3I Atlas, that requires an energy source. Option 1. Radioactive decay. Uranium, thorium, potassium, the long-lived isotopes that keep Earth's interior molten even after 4 or 5 billion years. But to heat a small object, you'd need unrealistic concentrations. You'd need the object to be made of ore-grade radioactive material which doesn't occur in nature. Option 2. Tidal heating. But 3I Atlas had no companion, no nearby planet flexing its interior. It was alone. Option 3. Residual formation heat. If the object formed recently, within the last few million years, it might still be warm from the accretion process, from impacts, from the heat of collapsing material. But interstellar objects are old. They've been wandering the galaxy for hundreds of millions of years, long enough for any formation heat to radiate away. Option 4. Crystallization heat. When amorphous ices transition to crystalline states, they release energy. Comets sometimes brighten suddenly when pockets of amorphous ice crystallize and release trapped volatiles. But that's a transient process. It happens once explosively, then stops. It doesn't sustain emissions over months. Option 5. Something else. Patel opened a new document and titled it Thermal Budget Analysis, 3I Atlas. He began with the simplest calculation. How much heat does the object receive from the sun, and how much does it radiate back? At 12 AU, the solar flux was about 950 watts per square meter. For an object 10 kilometers across with a spherical cross-section, that's roughly 75 million watts of incoming sunlight. Most of that is reflected. 3/Atlas had an albedo around 0.4, typical for comets, so only 4% was absorbed. That left about 3 million watts heating the surface. An object at that distance should reach an equilibrium temperature around 220 Kelvin, cold enough for water ice to be stable, warm enough for volatile ices like carbon monoxide to start sublimating. But if there was internal heat, the equilibrium would shift. Add just 50 kilowatts of internal heating, less than the power consumption of a typical house, and the surface temperature would rise by 10 to 15 Kelvin. Subtle. Detectable only with precise infrared observations. JWST's infrared spectrometer could measure that difference. But JWST wasn't scheduled to observe until November, and by then the object would be 1.8 AU away, fainter and colder. The signal would be harder to detect, ambiguous, debatable. Patel thought about Cassini again. The spacecraft hadn't just detected Enceladus's plumes, it had flown through them, sampling the composition directly, measuring the magnetic field, feeling the push of the jets against its thrusters. Close-up observation, in situ measurement, the only way to be sure. He opened the trajectory simulations that had been circulating since July. A fast flyby mission launched in October could reach 3I Atlas by late 2025, passing within a few thousand kilometers, close enough for high-resolution imaging, close enough to sample the coma, close enough to measure the magnetic field and particle environment. The delta-V budget was steep, about 15 kilometers per second, requiring multiple gravity assists and in-space refueling. The cost was estimated at $800 million, a bargain compared to flagship missions, but still a substantial commitment. And the political will was absent. He sent the analysis to a colleague at the Planetary Science Division. The reply came back within an hour. Interesting, but we're focused on Mars sample return and Europa Clipper follow-up. No appetite for another interstellar object mission, unless there's a smoking gun. Patel stared at that phrase, smoking gun. What would qualify? What level of anomaly would be enough? A signal that spelled out, hello, we are here. A propulsion signature. A resolved image showing manufactured structures. By the time any of those appeared, if they ever appeared, the object would be gone, receding at 43 kilometers per second. Unreachable. He thought about the principle of pre-adaptation. In biology, it's the idea that traits evolve for one purpose and later get co-opted for another. Feathers evolved for insulation, then were adapted for flight. Cassini was built to study Saturn, but its instruments were perfectly suited for characterizing Enceladus's ocean. We had the tools to characterize 3I Atlas. Infrared spectrometers, radio telescopes, fast spacecraft. We had everything except the timing. Science operates on proposal cycles measured in years. Missions are planned a decade in advance. but cosmic opportunities operate on windows measured in weeks. There's a fundamental mismatch, a structural inability to respond to transient phenomena that don't fit the schedule. Patel saved the document and filed it in a folder labeled Unfunded Concepts. Then he went back to his main project, analyzing decade-old data from a mission that had ended years ago, extracting the last insights from instruments that no longer existed, studying a moon that was still there, still venting, still waiting for the next spacecraft that might never come. Meanwhile, 3I Atlas continued its trajectory, spinning every 4 hours, emitting perhaps in patterns we couldn't see, warming perhaps from sources we couldn't measure, carrying secrets we had the tools to uncover but not the time. Chapter 3, October 2nd, Starship Flight 6 and the Rapid Response Problem. The roar began at dawn. At SpaceX's Starbase facility in Boca Chica, Texas, the sixth full-stack Starship stood on its launch mount, venting liquid oxygen into the humid Gulf Coast air. The vehicle was massive, 121 meters tall, the largest rocket ever built, powerful enough to lift 150 tons to low Earth orbit or send crewed missions to the Moon, Mars, and beyond. Flight 6 was a demonstration mission. No crew, no science payload, just a test of systems that, if they worked, would redefine what was possible in spaceflight: in-orbit refueling, extended coast phases, precision landing. The technologies needed for deep space exploration. The countdown reached 0 at 7:13 local time. 33 Raptor engines ignited simultaneously, and the vehicle lifted off with the slow, inevitable acceleration of something too large to be real. 30 seconds later, it was supersonic. 2.5 minutes later, the booster separated and began its descent back to the launch pad while the upper stage continued into orbit. The mission profile was ambitious. After reaching orbit, the upper stage deployed 6 Starlink satellites, demonstrating payload delivery. Then it performed a propellant transfer test, connecting to a prepositioned tanker spacecraft and transferring 40 tons of liquid methane and oxygen. The process took 8 hours. If it worked, it would prove that spacecraft could be refueled in orbit, extending their range far beyond what a single launch could achieve. It worked. At 19:42 UTC, SpaceX confirmed successful propellant transfer. The spacecraft undocked, fired its engines for a deorbit burn, and re-entered the atmosphere over the Pacific. 73 minutes later, it splashed down 200 kilometers off the coast of Hawaii, intact and recoverable. The mission was a milestone. It was also a reminder of what was possible when engineering moved faster than bureaucracy. In a small conference room at NASA's Goddard Space Flight Center, Dr. Sarah Kwan watched the landing on a wall-mounted screen. She was a mission planner, one of the people responsible for translating scientific goals into flyable trajectories, for calculating delta-V budgets and launch windows, for answering the question, can we get there? She'd been thinking about 3I Atlas for weeks. The trajectory simulations were still on her laptop, updated every few days as new observations refined the object's orbit. The latest version showed a narrow launch window extending through mid-October. After that, the geometry became unfavorable. The object would be too far, the alignment wrong, the fuel requirements beyond even Starship's capabilities. But if they launched now, if they could assemble a mission in the next 2 weeks, it was feasible. She'd run the numbers a dozen times. Starship could lift enough fuel to send a probe on a fast trajectory toward 3I Atlas, passing within 5,000 kilometers in late 2025. But the mission would require 3 in-orbit refueling events, 1 in low Earth orbit, 1 after a gravity assist from Venus, and 1 more during the cruise phase to adjust the trajectory. 3 refuelings, 3 rendezvous events, 3 chances for something to go wrong, and no payload. Not yet. There hadn't been time to design instruments, to build hardware, to test systems. The best they could do was repurpose an existing spacecraft, maybe one of the Mars orbiters sitting in storage, maybe a CubeSat platform equipped with cameras and spectrometers. It wouldn't be elegant. It wouldn't be a flagship mission with years of planning and peer review. It would be fast, risky, improvised. But it would get there. Quan had sent the proposal to the Planetary Defense Coordination Office in late September. The PDCO's mandate was to track near-Earth objects and develop mitigation strategies for potential impactors. 3I Atlas wasn't a threat. It was leaving the inner solar system, not approaching. But the office had broader authority to investigate unusual objects if they posed scientific interest. The response had been polite and non-committal. Interesting concept. We'll discuss at the next quarterly review. The next quarterly review was in November. By then, the launch window would be closed. She'd reached out to ESA, to JAXA, to the UK Space Agency, hoping for international collaboration. ESA was interested but faced procedural delays. Any new mission required approval from member states, and that process took months. JAXA was focused on its Martian moons exploration mission, launching in 2026. The UK Space Agency had no deep space capability. The Chinese National Space Administration had the resources and the political will to move quickly, but geopolitical tensions made collaboration difficult. Even informal data-sharing agreements took months to negotiate, and so the window narrowed. Quan pulled up the trajectory plot again. The red line showed 3I Atlas's path, arcing out of the solar system toward interstellar space. The blue line showed the optimal intercept trajectory, launched on October 15th, arriving in September 2025. There was a green line, too, a backup trajectory launched in November, arriving in March 2026. It required more fuel, took longer, and passed the object at a greater distance. Less ideal, but still possible. If they missed both windows, the next opportunity wouldn't come for years, when the object was too far, too faint, and too expensive to reach. She thought about Flight 6, about a rocket that went from concept to launch in 4 years, about an industry that iterated rapidly, failed publicly, and succeeded by moving faster than caution allowed. She thought about the phrase someone had used in a meeting. Science operates on proposal cycles measured in years, but cosmic opportunities operate on windows measured in weeks. There was a fundamental mismatch, a structural problem. The institutions designed to do careful, peer-reviewed, methodical science were not designed to respond to transient phenomena. They couldn't pivot quickly. They couldn't take risks. They couldn't launch a mission in 2 weeks, even when the opportunity was clear and the tools were ready. Her phone buzzed. An email from the PDCO. 3I Atlas fast flyby proposal, unable to proceed without funding allocation. Recommend resubmission in FY 2026 planning cycle. FY 2026, 2 years away. She closed the laptop and looked out the window. Somewhere above the horizon, invisible in the daylight, 3I Atlas was still moving, still receding at 43 kilometers per second, still carrying whatever had turned on, whatever had emitted those 47 minutes of radio light deeper into the dark. Later that day, she called a friend at SpaceX. Hypothetically, she said, if someone wanted to launch a deep space probe in 2 weeks using Starship, what would it take? There was a long pause. Depends, her friend said. Do you have a spacecraft? Not yet. Do you have funding? No. Do you have approval? No. Another pause. Then, so you're asking if we could launch a mission that doesn't exist, with money you don't have, to intercept an object that no one's sure is worth intercepting? Yes. Her friend laughed. I mean, technically, yeah, we could do it. We've got a booster stacked, we've got tankers in orbit, we've got launch infrastructure. If you showed up with a spacecraft and a check, we could probably get you off the ground in 3 weeks. But we won't. But you won't. Quan thanked her and hung up. That evening, she sat at her desk and wrote a memo titled, Institutional Barriers to Rapid Response in Planetary Science. It outlined the problem clearly. Transformative scientific opportunities were being lost not because of technical limitations, but because of procedural inertia. She listed examples. Oumuamua, missed because no mission could launch fast enough. Interstellar meteors, detected only in hindsight from archival data. Transient events that appeared and vanished while committees deliberated. She proposed solutions. A standing rapid response fund, pre-approved mission architectures, agreements with commercial launch providers for priority access. She sent the memo to her supervisor, to colleagues at other NASA centers, to researchers at ESA and JAXA. The responses were supportive. Everyone agreed. Everyone acknowledged the problem. No one had authority to fix it. And so 3I Atlas continued its journey. The launch window narrowed. The object receded. And somewhere in a storage facility in Colorado, a spacecraft that could have made the trip sat on a shelf, powered down, waiting for a mission that would never be assigned. This is not science fiction. This is early October 2024. Chapter 4, October 7th, The Iron Deficit. The spectrum arrived at 2:34 UTC, transmitted from the Subaru telescope on the summit of Mauna Kea. Dr. Yuki Tanaka had been observing 3I Atlas for 6 hours, using the high-dispersion spectrograph to capture light from the object's coma at wavelengths between 300 and 600 nanometers. The seeing was excellent, 0.4 arcseconds, and the object was just bright enough for high-resolution spectroscopy, magnitude 19.8, faint but detectable with long exposures. The goal was to measure the emission lines from metallic species, sodium, magnesium, calcium, iron, to characterize the coma's composition and compare it with other interstellar objects and solar system comets. The data reduction took 3 hours. When the process spectrum appeared on her screen, Tanaka spent 5 minutes checking for errors before accepting what she was seeing. Magnesium, strong. Multiple emission lines at 516, 7, 517, 3, and 518, 4 nanometers, consistent with neutral magnesium atoms excited by sunlight. Calcium, present. A single line at 422, 7 nanometers, weaker than magnesium but well above the noise. Sodium, faint. The D lines at 589, 0 and 589. 6 nanometers were barely detectable, close to the detection threshold. Iron absent. She zoomed in on the region where iron lines should appear, between 370 and 400 nanometers, where neutral iron has dozens of strong emission features. Nothing, just noise. Just the flat baseline of an empty spectrum. Tanaka ran the photometric calibration again. No change. She checked the wavelength calibration using telluric lines from Earth's atmosphere, perfect alignment. She checked for instrumental artifacts, for cosmic rays, for scattered light contamination. The absence was real. She pulled reference spectra from the literature, Comet Hale-Bopp, Comet Hyakutake, Comet ISON, all of them showed iron. Not as strong as sodium or magnesium, but present, detectable, measurable. The magnesium-to-iron ratio in typical comets ranged from 0.5 to 2, depending on composition and heliocentric distance. For 3I Atlas, she calculated an upper limit. If iron was present below the detection threshold, the magnesium-to-iron ratio had to be greater than 300 to 1. She sat back and stared at the spectrum. Magnesium and iron are geochemical twins. They originate from the same minerals, olivine, pyroxene, the silicates that make up rocky planets and asteroids. When those minerals are heated, by impacts, by solar radiation, by outgassing, they release both elements in roughly equal amounts. Finding magnesium without iron was like finding smoke without fire. Possible but strange. She opened the literature on planetary differentiation. When rocky bodies melt, dense elements sink to the core while light elements rise to the mantle. Earth's core is iron and nickel. The mantle is magnesium-rich silicates, olivine garnet perovskite. The crust is lighter still, feldspar, quartz, aluminum-rich minerals, but differentiation requires heat, sustained heat. Temperatures high enough to melt rock, above 1,200 Kelvin for silicates, higher for metals. And it requires gravity, pressure, time. Small bodies, asteroids, comets don't differentiate. They're rubble piles, loosely bound aggregates of dust and ice, never heated enough to melt, never large enough to compress. Unless they weren't small when they formed. There was a class of objects that could produce magnesium-rich, iron-poor material. The mantles of differentiated bodies. If a planetary embryo, something Mars-sized, formed early in the solar system, differentiated into core and mantle, and then was shattered by a giant impact, the fragments would be compositionally distinct. Core fragments would be iron-rich. Mantle fragments would be magnesium-rich. But 3I Atlas wasn't from our solar system. It was interstellar. Its trajectory, its velocity, its chemical composition, all pointed to an origin in another star system, light years away. And interstellar space is big. The odds of a fragment from a shattered exoplanet entering our solar system were vanishingly small. Not impossible. Oumuamua had arrived, after all, but rare enough that finding 2 in 5 years suggested we were living through an unusual time, or that we were only now learning to recognize them. Tanaka pulled up the spectroscopic database for 3I Atlas, compiled from dozens of observations over the summer. Every spectrum showed the same pattern. Strong magnesium, weak or absent iron. It wasn't a one-time anomaly. It was consistent, persistent, a fundamental property of the object's composition. She thought about the phrase that kept appearing in conversations, carefully worded, always qualified. Processed material. Processed implied refinement. Processed implied that the raw composition had been altered, separated, concentrated. Nature could do that. Differentiation was a natural process, but nature was inefficient. Nature produced gradients, mixtures, imperfect separations. This was clean, too clean. She drafted an email to the International Astronomical Union's Minor Planet Center, reporting the new spectroscopic data. She chose her words carefully. The mg/phi ratio in 3I Atlas exceeds 300. 1, significantly higher than any known comet. This composition is consistent with material derived from a differentiated planetary mantle. She didn't write, this composition is consistent with refined materials. She didn't write, this suggests industrial processing. But the implication was there, embedded in the numbers, waiting for someone to say it out loud. Meanwhile, in a university office in Zurich, a geochemist named Dr. Klaus Hoffmann read the spectroscopic report and ran his own calculations. He'd spent 20 years studying meteorites, the fragments of shattered asteroids that fall to Earth, carrying clues about the early solar system's composition. He knew the magnesium-iron systematics by heart. He knew that differentiated meteorites, fragments from the cores and mantles of ancient planetesimals, showed extreme ratios. Iron meteorites were nearly pure metal. Achondrites were silicate-rich, magnesium-dominated. But even achondrites had some iron. Even the most magnesium-rich samples from Vesta, the second-largest asteroid, a fully differentiated body with a basaltic crust, showed mg/phi ratios around 20. 1/300. One was unprecedented. He pulled up the geochemical fractionation models. To produce such extreme separation, you needed temperatures above 1,800 Kelvin, hot enough to vaporize iron preferentially, leaving magnesium behind. That could happen in impact plumes, in volcanic outgassing, in the superheated ejecta from giant collisions. But it was transient. It happened once, violently, and then cooled. It didn't persist for millions of years. It didn't survive the journey through interstellar space. Unless the separation happened recently. Unless 3I Atlas had been heated, processed, refined after it left its parent system. Hoffman opened a new document and began drafting a paper titled Geochemical Evidence for Thermal Processing in Interstellar Object 3I Atlas. He worked for 3 hours, citing meteorite studies, fractionation models, impact simulations. He built the case carefully, methodically, grounding every claim in established geochemistry. And then, in the conclusion, he wrote a single cautious sentence. If the observed mg/phi ratio is confirmed by future observations, it would imply either an extreme natural fractionation process not observed in solar system materials, or a compositional selection mechanism beyond current planetary science models. He read the sentence 3 times. Then he deleted beyond current planetary science models and replaced it with requiring further investigation. He saved the draft and sent it to 2 colleagues for review. Both responded within a day. Both said the data was solid, the analysis was rigorous, the conclusions were defensible. Neither of them mentioned the unwritten implication. That compositional selection mechanism was a careful euphemism for something no one wanted to say directly. That if you wanted to build something small and light, something that needed to travel far and fast, you might choose magnesium-rich materials. Low density, high strength, easy to work with. You might avoid iron, too heavy, too magnetic, unnecessary. You might refine your materials, select them, optimize them. The paper was submitted to Icarus on October 14th. It would be peer-reviewed, revised, accepted, and published in December. By then, 3I Atlas would be 23 AU from Earth, magnitude 21.5, accessible only to the largest telescopes. And the phrase process material would appear in 6 more papers, each one slightly bolder than the last. Chapter 5, October 12th, The Emergence. The first image came from Western Australia, at 4:12 local time. An amateur astronomer named David Chen was wrapping up a night of observing from his backyard in Perth. He'd been tracking 3I Atlas for weeks, hoping to capture images as the object emerged from solar conjunction. The last reliable observations had been in early September, before the object passed behind the sun. Now, more than a month later, it was finally visible again, low on the eastern horizon before dawn, a faint smudge of light in Virgo. Chen's telescope was modest, a 14-inch Schmidt-Cassegrain with a CCD camera, but the seeing was good, and he'd stacked 15 5-minute exposures to boost the signal. When the final image appeared on his laptop, he could see the object clearly. Magnitude 19.9, slightly dimmer than pre-conjunction observations predicted, but within the expected range. He posted the image to the Minor Planet mailing list with a brief note. 3I Atlas recovered. Position matches ephemeris. No obvious changes. 6 hours later, a professional observatory in Chile confirmed the detection. Then another in South Africa. By evening, a dozen observatories had captured post-conjunction images, and the astrometry was good enough to refine the orbit. The trajectory hadn't changed. 3I Atlas was still on course, still receding at 43 kilometers per second, still headed toward the same point in interstellar space. But something else had changed. The photometric data started arriving on October 13th. The Las Cumbres Observatory, a global network of robotic telescopes, had been monitoring the light curve for 48 hours, taking measurements every 30 minutes as the object rotated. When the data was compiled and plotted, the result was immediate and obvious. The light curve had 2 peaks. For 3 months from June through early September, the brightness had varied in a simple, sinusoidal pattern. 1 maximum, 1 minimum, repeating every 11.4 hours. That pattern was consistent with an elongated object tumbling in space, reflecting sunlight as its long axis rotated in and out of view. Now, the pattern was different. There was still a primary maximum, a bright peak occurring every 11.4 hours just as before, but there was a secondary maximum offset by 5-7 hours, exactly half the orbital period. The secondary peak was fainter, about 30% the brightness of the primary, but it was unmistakable. Dr. Lucas Mendez, a planetary scientist at the University of Chile, was the first to notice. He'd been analyzing 3-eye atlases photometry since June, and he knew the light curve by memory. When the new data appeared, it took him less than a minute to see the change. He pulled up the preconjunction data and overlaid it with the post-conjunction observations. The difference was stark. Before perihelion, 1 peak. After perihelion, 2 peaks. Something had changed. Something about the object's configuration, its shape, its surface, its activity. He ran the standard models. A contact binary, 2 lobes stuck together, could produce 2 peaks if each lobe had a different reflectivity. But the brightness ratio was wrong. Contact binaries usually produced peaks of similar amplitude. This was 3, 1, 2 asymmetric. A tumbling body in complex rotation could also produce multiple peaks, especially if it was irregularly shaped. But complex rotation states were chaotic, unstable, constantly evolving. The dual-peak pattern was too regular, repeating with clock-like precision over dozens of rotations. Fragmentation was another possibility. If the object had split during perihelion, broken by thermal stress, by outgassing forces, by tidal forces from the sun, the 2 fragments would produce 2 peaks. But fragmentation events were violent and chaotic. The fragments would drift apart, their orbits diverging over time. The light curve would show increasing separation, not stable periodicity. Mendez ran a shape model simulation, trying to fit an elongated, irregular body to the data. The model failed. No single shape could produce the observed pattern. The primary and secondary peaks had different amplitudes, different durations, different brightness profiles. It was as if there were 2 objects, not one. But there was only one object. Every image showed a single, unresolved point of light. If there were 2 fragments, they were too close together to separate, less than a few hundred kilometers apart, and they were moving in perfect synchrony, maintaining constant separation. Or something had deployed. Mendez stared at that word on his screen, deployed. It was the wrong word. It implied intentionality. It implied engineering. But it fit the data. If the object had extended something, a reflective panel, a secondary structure, a deployed appendage, it would create a second peak in the light curve. The primary body would rotate every 4 hours, producing the main brightness variation. The deployed structure would also rotate, but if it was offset from the rotation axis, it would catch sunlight at a different phase, producing a secondary peak. The timing was right, the stability was right, the asymmetry was right, and it explained why the change happened at perihelion. Close to the sun, temperatures are higher, thermal stresses are greater. If something was going to unfold, to extend, to activate, perihelion would be the logical time. Mendez drafted an email to the photometry working group. Post-perihelion light curve shows secondary peak at phase 0. 5. Possible explanations. 1. Complex rotation state. 2. Fragmentation with synchronized orbits. 3. Deployment of secondary structure. Recommend intensive monitoring. He deleted deployment of secondary structure. He rewrote it as emergence of secondary reflective surface. Better, neutral, descriptive without implying mechanism. He sent the email and waited. The responses came within hours. Other observers confirmed the dual-peak pattern. The data was solid. The change was real, and no one had a good natural explanation. Over the next 72 hours, the Las Cumbres network captured 180 brightness measurements, covering 15 complete rotations. The dual-peak pattern was stable. No drift, no chaos, no evolution. Whatever had changed was locked in place, rotating with the primary body, reflecting sunlight with consistent geometry. On October 16th, a researcher at Caltech ran a polarimetry analysis on the reflected light. Polarization measurements can reveal surface texture, Smooth surfaces produce different polarization signatures than rough surfaces. The primary peak showed low polarization, consistent with a rough, dusty surface. The secondary peak showed higher polarization, consistent with a smooth or specular surface, something shiny. The finding was included in a draft paper titled Photometric Evolution of 3I Atlas Through Perihelion Passage. The abstract noted, the post-perihelion light curve exhibits a stable secondary maximum inconsistent with known rotational states or fragmentation scenarios. Further observations are needed to constrain the geometry. The paper didn't mention deployment. It didn't mention engineering. It didn't mention the possibility that something on the object had opened, unfolded, turned on. But in the private email threads, in the Slack channels, in the late-night conversations between colleagues, the word started appearing, deployed. Because it was the simplest explanation, because it fit all the data, because everything else required stacking unlikely coincidences, invoking processes no one had ever observed, stretching natural phenomena beyond plausibility. And because for the first time since Oumuamua, the phrase natural origin was starting to feel like an assumption rather than a conclusion. Dr. Elena Vasquez at Berkeley read the photometry report and thought about the radio signal. 47 minutes of emission, occurring at rotational phase 0, 73. She pulled up the new light curve and marked phase 0, 73. It was near the primary peak, near but not exactly at maximum brightness. She marked phase 0, 23, exactly halfway around the rotation where the secondary peak occurred. The two phases were symmetric, opposite sides of the object, one side emitting radio waves, the other side reflecting light. As if one side was active and the other side was watching. She closed the data file and sat in the darkness of her office. Outside, the stars were invisible, drowned by city lights, but somewhere among them 6 AU away 3I Atlas was spinning, one side dark, one side bright, one side silent, one side speaking, and no one could agree on what it was saying. This is not science fiction. This is mid-October 2024. Chapter 6, October 18th, JWST's first look. The data arrived in segments, transmitted across 15 million kilometers from the James Webb Space Telescope's orbit at the L2 Lagrange point. JWST had observed 3I Atlas on October 16th during a brief scheduling window, using the near-infrared spectrograph to capture wavelengths between 0.9 and 5.3 microns, the thermal infrared, where warm surfaces glow and molecules reveal their chemical fingerprints. The observation was not easy. The object was faint, magnitude 21, receding at 17 AU from the Sun. JWST's pointing system had to track the object's motion precisely, integrating light for 6 hours to build enough signal. The raw data was 42 gigabytes, spectra, calibration files, detector diagnostics, and it took 48 hours to download and process. When the reduced spectrum appeared on Dr. Amelia Cross's screen at the Space Telescope Science Institute in Baltimore, she knew immediately that this was not a typical comet. The first thing she noticed was the 3.4 micron feature. It was an emission band, a broad hump in the spectrum where the object was emitting more light than expected. The wavelength was characteristic of aliphatic hydrocarbons, carbon-hydrogen bonds in chains and rings, the fundamental building blocks of organic chemistry. Organic molecules were common in comets. They'd been detected in dozens of objects: methane, ethane, methanol, formaldehyde, all products of the cold chemistry that happened in molecular clouds before stars and planets formed. Finding organics in 3I Atlas wasn't surprising, but the intensity was. The 3.4 micron band was strong, about 15% above the continuum. That implied a high abundance of hydrocarbons in the coma, much higher than typical comets. And the band was narrow, peaking sharply at 3.42 microns, consistent with a specific molecular structure rather than a mixture of many different species. Cross ran the spectral fitting software, comparing the observed band with laboratory spectra of known compounds. The best match was for CH stretching modes in aliphatic chains, molecules like octane, decane, long-chain hydrocarbons similar to those found in petroleum. That was strange. Comets typically showed simple molecules, 1 or 2 carbons, maybe 3. Long-chain hydrocarbons required more complex chemistry, more time, more energy to form. The second anomaly was at 4.6 microns. This feature was sharper, narrower, and completely unidentified. It didn't match any of the standard cometary molecules: water, ice, carbon dioxide, methane, ammonia. It didn't match polycyclic aromatic hydrocarbons, the soot-like molecules common in interstellar space. It didn't match silicate dust, organic tars, or any of the 100 other compounds in the spectroscopic database. Cross spent 3 hours searching the literature. She checked laboratory spectra from astrobiology experiments, from meteorite studies, from industrial chemistry databases. The closest match was to nitrile compounds, molecules with carbon-nitrogen triple bonds, but the wavelength was slightly off, and nitriles required nitrogen-rich environments that didn't exist in typical comets. She called a colleague at NASA's Goddard Astrobiology Institute. "I need help identifying a spectral feature," she said, sending over the data. "For 6 microns, sharp, strong, doesn't match anything I've seen." Her colleague analyzed it for 20 minutes, then called back. "It's close to the CN stretch in isocyanates," he said, "or maybe certain amino acid precursors. But you'd need concentrated nitrogen chemistry, and you'd need heat, maybe 300 Kelvin, to populate the excited states that produce emission. The object's surface temperature is only 220 Kelvin. Then the emission is coming from somewhere warmer, subsurface, interior." Cross thought about the thermal excess that had been reported in preliminary JWST data, the long wavelength emission suggesting internal heat. If the interior was warm, if there were pockets of heated material outgassing through vents or cracks, those regions could be hot enough to excite molecular vibrations. But that raised another question. Why were the molecules confined to specific regions? Why weren't they distributed throughout the coma? She pulled up the spatial distribution maps, images showing where in the coma the different spectral features were coming from. Most of the 3-4 micron emission was concentrated near the nucleus, within a few hundred kilometers of the central body. The 4-6 micron feature was even more localized. It appeared to come from a single region on the sunlit hemisphere, a bright spot that rotated in and out of view with the object's 11.4-hour period, a localized emission region, tied to rotation, appearing and disappearing with clock-like regularity. Cross marked the rotational phase when the 4-6 micron emission was brightest, phase 0, 74. She pulled up the photometry data, the radio detection times, the spectroscopic observations from the summer. Phase 0, 74 was the same phase where the radio signal had been detected, the same phase where the mysterious ghost lines appeared, the same phase where everything anomalous seemed to happen. One side of the object, one active region, one hemisphere that was different from the rest. She drafted a report for the JWST science team. NIRS-spec observations reveal strong organic emission at 3-4 microns and an unidentified feature at 4-6 microns. Emission is localized and phase-dependent. Composition is inconsistent with typical cometary volatiles. Possible explanations include subsurface outgassing from a warm interior or localized surface chemistry driven by solar heating. She sent the report at 18:30 UTC on October 18th. By 20:00, it had been forwarded to 16 research groups. By 22:00, a science journalist had received a leaked summary. By midnight, the headlines began appearing. Interstellar object shows organic chemistry. JWST, detects unknown molecules in 3I Atlas. Does the mysterious comet contain amino acids? The research team scrambled to respond. Press releases were drafted, clarifications issued, interviews declined. The message was consistent. Organic molecules are not life. The detection is ambiguous. The features could be natural. But the public conversation had already shifted. For the first time, the phrase biosignature entered the discourse. Not from scientists, most were careful to avoid the word, but from commentators, from bloggers, from people who saw the headlines and made the leap. Organic molecules, nitrogen chemistry, amino acid precursors, the ingredients of life. It didn't matter that the molecules weren't alive. It didn't matter that similar chemistry occurred in dead comets, in lifeless asteroids, in interstellar clouds where nothing had ever evolved. The narrative was too compelling. An interstellar visitor carrying organic compounds, exhibiting anomalies, emitting signals. By October 20th, 3 major news networks had run stories. By October 22nd, a U.S. congressman had called for increased funding to study the object. By October 24th, a poll showed that 34% of Americans believed 3I Atlas might be artificial. Dr. Cross sat in a conference room at St. SCI, fielding questions from reporters who didn't understand spectra, from administrators who wanted clear answers, from colleagues who were frustrated that the careful language of science had been translated into sensationalism. Are the molecules consistent with life? One reporter asked. Organic molecules are precursors to life, Cross said carefully. But they're also produced by non-biological processes. We see them everywhere, in comets, in interstellar clouds, in meteorites. Their presence doesn't imply biology. But could they be from biology? Anything is possible. But the simplest explanation, the explanation most consistent with what we know, is that these are natural products of interstellar chemistry. What about the unidentified feature at 4.6 microns? Cross hesitated. We're still working on identifying it. It could be a nitrile, an isocyanate, or a molecular species we haven't encountered before. Further observations will help narrow down the possibilities. Is it possible that the object is artificial? And there it was. The question no one wanted to ask directly, phrased carefully, hedged with caution. Cross chose her words precisely. The observations are consistent with a natural origin. We have not detected any features that require invoking non-natural explanations. It was a true statement. It was also incomplete, because the observations were also consistent with something else, with localized heating, with organized emission, with chemistry that happened in the right place at the right time with the right geometry. The press conference ended at 14. Cross returned to her office and pulled up the spectrum again. The 4.6 micron feature was still there, sharp and bright, unexplained. She thought about a conversation she'd had with a biochemist a few days earlier. He'd been reviewing the spectrum, looking for anything that matched biological molecules, and he'd made an offhand comment. You know, 4.6 microns is also near the absorption band for certain peptide bonds. Peptide bonds, the chemical linkages that connect amino acids into proteins. But that's absorption, not emission, Cross had said. Right. Unless the molecules were warm, then you'd get emission. She hadn't thought much about it at the time. Peptide bonds required life, and no one was seriously suggesting that 3I Atlas was alive. But now, sitting alone in her office, staring at the spectrum, she allowed herself to consider the possibility. Not life, but chemistry that life used. Chemistry that was efficient, versatile, functional. Chemistry that, if you were designing a system to withstand the cold and radiation of interstellar space, you might choose. Because organic molecules were stable, nitrogen chemistry was robust, peptide-like bonds were strong and flexible. And if you needed materials that could self-repair, that could adapt, that could function across a wide range of temperatures, Biochemistry offered solutions that no metal or ceramic could match. She didn't write any of this down. She didn't share it with colleagues. She filed it in the part of her mind reserved for ideas that were too speculative to say out loud. But the thought stayed with her. And later, when she looked up at the night sky, she wondered if somewhere out there, 17 AU away, something was looking back. This is not science fiction. This is late October 2024. Chapter 7, October 24th. The rotation anomaly deepens. The drift was subtle, almost invisible. For 2 weeks, the Las Cumbres Observatory Network had been monitoring 3I Atlas's light curve, taking brightness measurements every 30 minutes as the object rotated. The dual-peak pattern was stable, primary maximum at phase 00, secondary maximum at phase 05, repeating every 4 hours with extraordinary regularity. But Dr. Sofia Ramirez, an orbital dynamicist at MIT, noticed something strange. The secondary peak was drifting, not by much, not in a way that would be obvious from a few nights of data. But when she compiled 2 weeks of observations and fit a precise ephemeris to the light curve, the pattern became clear. The time interval between the primary and secondary peaks was increasing by 0.3 hours per day. That's 10.8 seconds per day, less than 0.2% of the rotation period. Tiny, negligible, except it wasn't negligible, it was systematic, persistent, measurable. Ramirez ran the calculations 3 times to make sure she wasn't seeing an artifact. Same result. The secondary peak was occurring slightly later each day, drifting slowly away from the exact half-period mark. At the current rate, in 30 days the offset would be 0.9 hours, about 5.5 minutes. In 100 days, the secondary peak would be 18 minutes late. She pulled up the shape models and rotation simulations. If the object were a rigid body, a single piece of rock or ice tumbling in space, the rotation should be perfectly stable. Angular momentum is conserved. There are no forces in empty space to speed it up or slow it down. The light curve should repeat with clock-like precision, unchanged for millions of years. But this wasn't rigid body rotation. The drift implied that something about the object's configuration was changing. Either the mass distribution was shifting, or something was exerting torque, or the secondary structure producing the light curve peak was moving relative to the primary body. Option 1. Precession. Like a spinning top wobbling on a table, a rotating object can precess if its angular momentum vector is not aligned with its symmetry axis. Precession changes the orientation gradually over time, which can shift the timing of brightness peaks. Ramirez ran a precession model. It required very specific conditions, a particular mass distribution, a particular spin state, and it produced a drift rate several times slower than observed. Close but not right. Option 2. Outgassing torque. When volatile material sublimates from a comet's surface, the escaping gas exerts a small rocket-like force. If the outgassing is asymmetric, stronger on one side than the other, it creates a torque that changes the rotation state. Outgassing torques were well documented. They'd been observed on Comet 67P during the Rosetta mission, causing the nucleus to spin up and wobble as jets of water vapor erupted from active regions. But outgassing torques were chaotic. They varied with solar distance, with surface temperature, with the location and activity of different jets. They didn't produce smooth, linear drifts. They produced jerks, fluctuations, unpredictable changes. The drift in 3I Atlas's light curve was smooth, linear, predictable. Option 3, something was moving. Ramirez opened a new simulation and modeled the simplest scenario, a binary system. 2 objects orbiting each other, bound by gravity, producing 2 brightness peaks as they rotated. If the orbit was decaying, if the 2 objects were slowly spiraling together due to tidal forces, the orbital period would decrease, and the time between peaks would drift. But tidal decay required close proximity and significant tidal forces. The two objects would need to be within a few hundred kilometers of each other, and one of them would need to be large enough to raise tides on the other. 3I Atlas was small, maybe 10 kilometers across. Its gravity was negligible. Tidal forces would be weak, and tidal decay would take millions of years, not weeks. She ran the numbers anyway. The drift rate required the two objects to be approaching each other at about 2 meters per day. That was fast, far faster than any natural tidal decay process, unless something was pulling them together. Unless there was a force beyond gravity. She deleted that line from her notes. Option 4. Deployment. If the secondary peak was caused by a structure that had extended from the primary body, a reflective panel, a boom, a deployed appendage, and if that structure was slowly moving relative to the main body, it would produce exactly the observed drift. The structure could be rotating faster than the primary body, or slower, or precessing independently. It could be extending further, or retracting, or changing its orientation. Any of those motions would shift the timing of the secondary brightness peak. Ramirez ran a simple model, a primary body rotating every 4 hours, and a secondary structure rotating at a slightly different rate, 403 hours. The beat frequency between the two rotation periods would create an apparent drift of 0.3 hours per day, perfect match. She sat back and stared at the simulation. It fit the data. It explained the drift. It was the simplest model that worked, but it required the secondary structure to have independent rotation. It required two different rotation rates, maintained simultaneously over weeks of observation. Natural objects didn't do that. Contact binaries rotated as a unit. Fragments from fragmentation, events drifted apart. Tumbling bodies settled into minimum energy states where everything rotated together. Only designed systems maintained independent motion. Only engineered structures, solar panels, antennas, sensor booms, rotated separately from their parent spacecraft. She opened a draft email to the photometry working group, typing. Analysis of the dual peak light curve shows systematic drift of 0.3 hr/day, inconsistent with rigid body rotation or natural torques. Best fit model requires. She stopped. Required what? Independent rotation, deployment, engineering. She rewrote the sentence. Best fit model suggests complex rotational dynamics not fully explained by current natural models. Further observations are recommended. Safer, vaguer. True but incomplete. She sent the email and waited. The responses came quickly. Other astronomers confirmed the drift. Some proposed variations of the precession model. Others suggested binary scenarios. No one explicitly mentioned deployment, but the word was there, implied, hovering between the lines. A researcher at Johns Hopkins ran a different analysis, looking not at the timing but at the shape of the secondary peak. He found that the peak's amplitude was slowly increasing, about 1% per week, as if the secondary structure was becoming more reflective, or growing larger, or orienting itself more favorably toward the sun. A researcher at ESA looked at the spectroscopic data and noticed that the 4-6 micron emission feature was also drifting slightly in wavelength, redshifting by about 0.1 microns per week. Redshift implied motion away from the observer, radial velocity. If the emission was coming from a structure moving outward from the primary body, that would explain the redshift. If the structure was extending, deploying, unfolding, the motion would be outward. None of these findings were conclusive. Each one had multiple interpretations, but together they painted a picture. Something on 3I Atlas was changing. Not chaotically, not randomly, gradually, systematically, as if following a plan. On October 28, Dr. Ramirez received an email from a colleague in orbital mechanics. The subject line read, Ray. 3I light curve drift analogy. The message was brief. Your drift analysis reminded me of something. Check out Voyager 1 scan platform deployment, 1979. Independent rotation, similar drift rate. Obviously different context, but the dynamics are analogous. Ramirez pulled up the Voyager mission archives. In 1979, as Voyager 1 approached Jupiter, its scan platform, a movable boom carrying cameras and spectrometers, was repositioned to track the planet during the flyby. The platform had independent motors, allowing it to rotate separately from the main spacecraft. The light curve from Voyager during that period showed a primary peak from the spacecraft body and a secondary peak from the scan platform, with a slow drift as the platform adjusted its orientation. The dynamics were indeed analogous. The difference was that Voyager was a spacecraft, built by humans, controlled by engineers, designed to move independently. 3I Atlas was a comet from another star system, uncontrolled, natural. Wasn't it? Ramirez closed the email and sat in silence. Outside her window, the lights of Cambridge glowed against the October sky. Somewhere above those lights, invisible and impossibly far, 3I Atlas was spinning, drifting, changing, and no one could agree on why. Chapter 8, October 29th. The shutdown continues. The observatory dome remained closed. At the Very Large Array in New Mexico, 27 radio dishes sat idle, locked in maintenance mode while technicians upgraded the signal processing systems. The work was scheduled months in advance, necessary for future observations, non-negotiable. The upgrade would take 3 weeks. During that time, the VLA, one of the most powerful radio telescopes in the world, could not observe 3I Atlas. It was the third major facility to go offline in October. The European Extremely Large Telescope, under construction on Cerro Armazones in Chile, had been delayed by 6 months. Budget shortfalls, supply chain disruptions, and bureaucratic delays pushed the completion date from late 2025 to mid-2026. When it finally opened, it would be the largest optical telescope ever built, capable of detecting objects 10 times fainter than current instruments. But it wasn't open yet, and by mid-2026, 3I Atlas would be beyond the orbit of Jupiter, magnitude 24, too faint even for the ELT. The Chinese space station telescope had the aperture and the positioning to observe 3I Atlas even during solar conjunction. Its orbit, trailing the Chinese space station in low Earth orbit, but occasionally boosted to higher altitudes for deep space observations, gave it unique visibility of near-solar targets. But access was limited. The telescope was a national asset, and observing time was allocated to domestic research programs. External requests required months of negotiation, formal proposals, diplomatic coordination. A coalition of international astronomers had submitted a request in early October, asking for 10 hours of observing time to capture high-resolution spectra of 3I Atlas. The request was reviewed, acknowledged, and placed in the queue. The response came on October 29th. Request cannot be accommodated during the current observing cycle. Please resubmit for cycle 3, beginning in March 2025. By March, the object would be gone. Dr. Marcus Chen, an astronomer at the University of Toronto, read the email and felt the familiar frustration of science constrained by bureaucracy. He'd spent 20 years studying transient phenomena, supernovae, gamma-ray bursts, tidal disruption events, objects that appeared suddenly, evolved rapidly, and disappeared before you could schedule observing time. He'd learned to be fast, to be opportunistic, to use whatever telescopes were available. But even flexibility had limits. The big telescopes, the ones with the sensitivity to detect faint objects, the resolution to separate fine details, the wavelength coverage to identify molecules, were oversubscribed. Demand exceeded supply by factors of 5, 10, sometimes 20. Getting time required submitting proposals months in advance, going through peer review, competing with hundreds of other projects. The system worked well for predictable science, for objects that would still be there in 6 months, for questions that could wait. It didn't work for 3I Atlas. Chen opened his email and began drafting a message to the small observatory network. University telescopes, private facilities, amateur astronomers that had been coordinating their own observations. The telescopes were modest, the data noisy, but they were available, flexible, persistent. CSSD denied, he wrote. VLA offline until mid-November. ELT delayed, we're on our own. He sent the message and waited. The responses came within hours. From Hawaii, Keck can give us 4 hours next week. Not much, but it's something. From Australia, Anglo-Australian telescope available, scheduling 2 nights of spectroscopy. From South Africa, SALT has a gap in the schedule. We can fit in 6 hours if the weather holds. From backyard observatories around the world, dozens of messages offering time, data, collaboration. The quality varied. Some of the equipment was professional grade, some was amateur, but the commitment was universal. If the institutions wouldn't observe, the grassroots would. Chen compiled the offers into a coordinated observing plan. Photometry every night, spectroscopy when possible, radio monitoring with smaller arrays. The data would be patchy, incomplete, but it would be continuous. And continuity mattered, because 3I Atlas was still changing. The light curve drift, the spectral evolution, the thermal excess. Whatever was happening, it was happening now, and if they stopped watching, they'd miss it. Meanwhile, in a university office in New Zealand, a graduate student named Lena Park was alone at a small observatory, operating a 1-meter telescope that had been built in the 1970s and refurbished with a modern CCD camera. She'd been following the 3I Atlas story since June, reading every paper, every observation report, every speculative email thread. She wasn't part of the main research teams. She was a master's student studying stellar populations, barely connected to the planetary science community. But she was curious. And she had telescope time. On the night of October 29th, under clear skies and good seeing, she pointed the telescope toward 3I Atlas and began integrating. The object was faint, magnitude 20.2, and it took 3 hours to build enough signal for spectroscopy. When the spectrum appeared on her screen, she almost dismissed it. There was a line, narrow, sharp, bright, at 487, 9 nanometers. One of the ghost lines. She checked the wavelength calibration. Solid. She checked for instrumental artifacts. None. She checked the object's position. Correct. The line was real. Park sat in the dim glow of her computer screen, alone in the observatory dome, staring at the spectrum. She'd read about the ghost lines, the unidentified emission features that appeared intermittently in the summer observations. She knew they were controversial, ambiguous, unexplained. And now she detected one. She saved the data and sent an email to Dr. Chen with the subject line, 487, 9 nm line detected New Zealand. Then she sat back and waited for dawn. By the time the sun rose, her email had been forwarded to 40 researchers across a dozen countries. The spectrum had been analyzed, verified, discussed. The ghost line was back. And this time, it had been detected not by a flagship facility with cutting-edge instruments, but by a graduate student at a 50-year-old telescope in the southern hemisphere, working alone, driven by nothing but curiosity. It was a reminder of something important. Discovery doesn't require billion-dollar budgets. It requires attention, persistence, the willingness to look when everyone else has moved on. The grassroots network expanded. More observers joined. More data accumulated. The light curve, the spectra, the radio monitoring, everything was being recorded, archived, shared. The big telescopes might be offline. The major facilities might be delayed. But the sky was still open. And somewhere, 18 AU away, 3I Atlas continued its journey. Spinning. Changing. Emitting signals that a graduate student in New Zealand could detect with a half-century-old telescope. If one person, working alone, could see it, then it was bright enough to matter. And if it mattered, then someone somewhere would keep watching. This is not science fiction. This is late October 2024. Chapter 9, November 3rd. The second radio event. The signal appeared at 19:23 UTC during the evening shift at FAST. The 500-meter aperture spherical telescope, the largest single-dish radio telescope in the world, had been tracking 3I Atlas for 2 hours, monitoring the 1612 MHz hydroxyl line in case the September emission repeated. It didn't. Instead, at 19:23, a different line appeared, 1665, 402 MHz. The frequency was immediately recognizable. It was another hydroxyl maser line, one of the 4 ground state transitions of the OH radical, offset from the 1612 line by 53 MHz. The detection was strong, 6 sigma above the noise floor, clear, unmistakable, impossible to dismiss as interference or artifact, and it had the same characteristics as the September signal, narrow bandwidth 2.6 kHz, high frequency stability 0.1 Hz, and sharp cutoff after 38 minutes. Dr. Wei Zhang, the FAST project scientist leading the observation, immediately called for follow-up. The telescope remained locked on 3I Atlas for another 4 hours, but the signal did not return. By midnight UTC, the object had set below the horizon, and observation ended. Zhang pulled the data and began the analysis. The signal's Doppler shift matched 3I Atlas's velocity within 0.1 km/s, perfect agreement, ruling out terrestrial interference. The timing matched the object's rotation period. The emission occurred at rotational phase 0.73, exactly where the September signal had appeared. Same phase, same characteristics, different frequency. He opened the literature on hydroxyl masers and began reading. OH masers occur naturally in space, typically in regions where water molecules are dissociated by ultraviolet light. The 4 ground state transitions, at 1612, 1665, 1667, and 1720 MHz, emit under different physical conditions. The 1612 line is brightest in cold, diffuse environments. The 1665 and 1667 lines are brightest in warm, dense regions. The 1720 line appears in shocked gas, compressed by supernova remnants or colliding clouds. The conditions required for different lines were well characterized, and they were mutually exclusive. You didn't see 1612 and 1665 lines from the same region, unless something was driving the system out of equilibrium. Zhang pulled up the plasma physics models. Hydroxyl masers are pumped by radiation. UV photons excite the OH molecules into higher energy states, and they decay by emitting radio waves. The relative brightness of the 4 lines depends on the radiation field, the gas density, the temperature. For both 1612 and 1665 lines to emit from the same object, the pumping conditions would need to vary rapidly, changing from cold and diffuse to warm and dense within a few weeks. Or the emission regions would need to be different, each tuned to produce a specific line. He calculated the implied magnetic field strength. The spacing between the 1612 and 1665 lines, 53 MHz, was determined by the Zeeman splitting of the OH radical in a magnetic field. To produce both lines simultaneously required a field strength of approximately 0.1 Tesla, about 10 times stronger than Earth's surface field. Natural comets don't have magnetic fields like that. Their nuclei are non-magnetic, mixtures of ice and rock with no significant metallic content. The coma is ionized by sunlight, and the flowing plasma can generate weak induced magnetic fields, but they're typically 1,000 times weaker than what was required here. To generate a 0.1 Tesla field, you needed magnetized material, iron cores, magnetite grains, or electrical currents, but 3I Atlas was iron poor. Spectroscopy had confirmed it. Magnesium-rich, iron absent. No cores, no magnetite. That left electrical currents. Zhang opened a magnetohydrodynamics textbook and reviewed the equations. Moving plasma generates magnetic fields. If charged particles flow in a loop, a current, they create a field perpendicular to the flow. The strength of the field depends on the current density and the size of the loop. He ran the numbers to generate a 1 Tesla field over a region a few hundred meters across required a current of approximately 10,000 amperes. For context, a typical household circuit carries 15 amperes. The power grid in a small city carries thousands of amperes. The aurora borealis, one of nature's most spectacular electrical displays, is driven by currents of a few million amperes flowing across thousands of kilometers. 10,000 amperes in a few hundred meters was intense, concentrated, sustained, and it required power. The resistance of ionized gas is low but non-zero. To maintain a 10,000 ampere current against that resistance required continuous energy input, approximately 10 kilowatts, assuming reasonable estimates for plasma conductivity and current path geometry. 10 kilowatts, about the power output of a large diesel generator, not enormous but not trivial either, and it had to be sustained. The magnetic field didn't flicker, it didn't fade. It maintained the precise conditions needed to generate hydroxyl maser emission for 38 minutes, then stopped abruptly. Zhang wrote a draft report. Fast detection of 1665 MHz OH emission from 3I Atlas. The abstract noted the detection, the timing, the frequency stability. The discussion section explored the plasma physics, the magnetic field requirements, the energy budget. And then in the final paragraph he wrote, "The observed emission characteristics are consistent with stimulated maser activity in a magnetized plasma environment. The required magnetic field strength, 0.1 T and inferred power input 10 kW, are difficult to reconcile with passive cometary processes. Alternative mechanisms, including active plasma confinement, warrant further investigation." He read the paragraph 3 times. Active plasma confinement was careful language. It didn't say artificial. It didn't say engineered. But it implied control. It implied that something was generating, confining, and maintaining the plasma in conditions that natural processes struggled to explain. He sent the draft to his supervisor at the Chinese Academy of Sciences. The reply came the next day. Findings are significant. Recommend peer review before public release. Be cautious with speculation. Zhang revised the draft, softening the language, removing active plasma confinement and replacing it with non-thermal energy input. Better, vaguer, less provocative. The revised report was submitted to the IAU Central Bureau and to several peer-reviewed journals. It would be weeks before publication, months before full peer review. But the data was archived, and within days, word spread through the radio astronomy community. A second emission line, a different frequency, the same timing, the same precision. Dr. Elena Vasquez at Berkeley received the report and pulled up her own detection from September. She overlaid the two signals, 1612 MHz and 1665 MHz, and examined the characteristics. Bandwidth nearly identical, stability nearly identical, duration similar within 10%. The only difference was frequency. She thought about transmitters, about lasers and masers, about systems designed to emit specific frequencies with high precision. Natural masers were remarkable, nature's own amplifiers, converting ambient radiation into coherent radio waves. But natural masers were chaotic, variable, driven by changing conditions in their environment. These emissions were stable, repeatable, precise. She ran a simulation modeling the plasma physics, trying to find natural conditions that could produce both lines. The simulation required fine-tuning, precise magnetic field strengths, precise densities, precise temperatures. Change any parameter by 10% and the emission stopped or shifted to a different frequency. It was possible, but it required the system to maintain exquisitely balanced conditions over weeks, across two separate emission events. That kind of stability was rare in nature. That kind of stability was typical in engineering. Vasquez saved the simulation and closed her laptop. She thought about the phrase that kept appearing in private conversations, never written down, never said publicly: organized emission. Organized meant non-random. Organized meant controlled. Organized meant that somewhere, somehow, something was generating radio waves with a degree of precision that natural chaos rarely achieved. And now it had happened twice. She pulled up the rotation ephemeris and calculated the next occurrence of phase 0. 73. November 12th, 04:15 UTC. If the pattern held, if the emissions continued to repeat, the next signal should appear then. She sent an alert to every radio telescope that could observe. Predicted emission window, November 12th, 4:00:05 UTC. Frequencies of interest: 1612, 1665, 1667, 1720 MHz. Priority observation recommended. Then she waited. Somewhere 19 AU from Earth, 3I Atlas continued its rotation. One side facing the sun, one side in shadow, one side emitting radio waves at frequencies determined by magnetic fields, by plasma physics, by conditions that required power and control. And in 10 days that side would face Earth again. If the pattern held, they'd know. If the pattern broke, they'd have new questions. Either way, the story was not over. This is not science fiction. This is early November 2024. Due to length constraints, I'll continue with the remaining chapters in the next section. We're at approximately 11,000 words so far, and I'll complete the remaining -11,000 words to reach the 22,000-word target. Chapter 10, November 9th, The Alignment Hypothesis. The pattern emerged from the data like a hidden image slowly coming into focus. Dr. Jin Park, a data scientist at the SETI Institute, had been analyzing 3I Atlas's trajectory corrections since July. She wasn't part of the primary observation teams. Her work focused on signal processing and pattern recognition, but she'd been following the object's story with increasing interest. The trajectory corrections were subtle. Small velocity changes, a few centimeters per second, maybe a tenth of a meter per second at most, detected through precise astrometry and Doppler measurements. Each correction was barely above the noise threshold, easy to dismiss as measurement uncertainty or natural outgassing effects. But Park had access to something most astronomers didn't: machine learning algorithms designed to find patterns in noisy data. She developed the algorithms for SETI work, training neural networks to identify structured signals in radio telescope data, faint transmissions buried in noise, patterns that human eyes might miss. The algorithms looked for regularities, for correlations, for anything that suggested organization rather than randomness. She fed the trajectory data into the system. 3 days later, the algorithm flagged a result. The trajectory corrections, when projected forward in time, aligned the object's future position with a specific point in space. Not a planet, not a star, a coordinate in interstellar space approximately 240 light-years from the Sun, in the direction of the constellation Lyra. Park pulled up the star charts. The coordinate was empty: no bright stars, no catalogued exoplanets, no obvious destinations. Just a patch of sky 12 degrees north of Vega, unremarkable and uninteresting. But the alignment was statistically significant. Each correction, applied at the observed times, nudged the trajectory slightly toward that coordinate. The margin of error was about 5 degrees, large enough to be uncertain, small enough to be suggestive. She ran the Monte Carlo simulations, testing whether the alignment could be coincidental. Random trajectory corrections, applied at random times, would point in random directions. The probability that they'd all point within 5 degrees of the same coordinate was about 1 in 400. Low probability, but not impossible. She checked the projection. If 3I Atlas continued on its current trajectory, making no further corrections, it would pass within 3 degrees of the target coordinate in approximately 8,000 years. 8,000 years. A long time by human standards, a blink by cosmic standards. Park saved the analysis and drafted an email to the 3I Atlas Research Network. She chose her words carefully. Trajectory analysis suggests that observed velocity corrections may be non-random. When projected forward, the object's path aligns within ~5 degrees of a coordinate in Lyra, Ra 19H12M, Dec plus 39 degrees 4. Statistical significance, P0, 25. This finding is preliminary and should be interpreted with caution. However, if future corrections refine the alignment, the probability of coincidence will decrease rapidly. She attached the data, the plots, the Monte Carlo results. Then she hesitated before sending. The implication was obvious. If the corrections were refining an alignment, if they were steering the object toward a specific destination, then they weren't natural. They were controlled. She reread the email. The language was neutral, descriptive, grounded in statistics. She wasn't claiming intentionality. She wasn't saying the object was navigating. She was just reporting the data. She sent the email at 14:37 UTC on November 9th. Within an hour, 23 people had read it. Within 2 hours, the first reply arrived. Jin, this is fascinating. Can you share the code? I want to verify the statistics independently. Within 4 hours, 3 independent teams had confirmed the alignment using their own trajectory data and analysis methods. By evening, the finding was being discussed in a dozen group chats and email threads. Dr. Amir Patel at JPL pulled up the coordinate in the mission planning software he used for interstellar probe studies. The region was empty, as Park had reported. No stars brighter than magnitude 9, no known exoplanets, no molecular clouds. But that didn't mean it was empty. He cross-referenced the coordinate with the Gaia star catalog, which had mapped over 1 billion stars with unprecedented precision. Within 5 degrees of the target coordinate, there were 847 stars, most of them faint red dwarfs, too dim for ground-based surveys. He filtered the list. Stars within 300 light-years, spectral types suitable for planets, no known brown dwarf companions. That left 92 candidates. He cross-referenced those with the NASA Exoplanet Archive. 7 of the stars had been observed by Kepler or TESS, the transit-hunting telescopes that had discovered thousands of exoplanets. None showed confirmed planets, but that didn't mean planets weren't there, only that they hadn't been detected yet. Most exoplanets were still unknown. The surveys had barely scratched the surface. Patel opened a new document and began drafting a target list, candidate destinations for 3I Atlas. He listed the 7 stars with observational data, noting their distances, spectral types, and ages. Then he stopped. What was he doing? He was planning follow-up observations for stars that might be aligned with an object's trajectory. Based on corrections that were barely detectable, based on an alignment that could still be coincidental, he was treating 3I Atlas as if it were a spacecraft. He closed the document without saving, but the thought stayed with him. Dr. Sofia Ramirez at MIT saw Park's email and immediately thought about the light curve drift. She'd been tracking the secondary peak slow migration, 0. 3 hours per day, steady and linear. If the object was making trajectory corrections, if it was actively navigating, then the light curve drift might not be a passive effect. It might be deliberate, a reorientation, an adjustment. She pulled up the timing. The light curve drift had started around October 12th, the same time the dual peak pattern emerged. The trajectory corrections had been detected throughout September and October, overlapping timescales, overlapping changes. She ran a calculation. If the secondary structure was a control surface, something that could exert torque, change orientation, adjust trajectory, how much force would it need to produce? Surprisingly little. In the vacuum of space, even a small force applied continuously could change velocity significantly over time. A thrust of 1 Newton, about the force of an apple resting in your hand, applied for a week, could change velocity by a few centimeters per second. The observed trajectory corrections were consistent with forces of a few newtons, small, subtle, but enough, and the timing matched the light curve changes. Ramirez opened a new simulation and modeled the scenario. A primary body rotating every 4 hours and a secondary structure, call it a control surface, that could orient itself independently. By changing its angle relative to the sun, the surface could exert radiation pressure, a tiny push from sunlight hitting the reflective material. The simulation worked. The forces were right. The timing was right. The drift in the light curve matched the expected reorientation. She saved the simulation and sat back. It was the simplest model that fit all the data. It explained the trajectory corrections, the light curve drift, the secondary peak slow migration. But it required the control surface to be articulated, mobile, responsive. It required engineering. She didn't write that in her notes. She didn't share the simulation with colleagues. She filed it in the same mental folder where she'd been collecting all the other pieces that fit together too neatly to be natural, but too strangely to be comfortable. That evening, Dr. Jin Park received an email from a colleague at the European Southern Observatory. The subject line read, "Ray, alignment hypothesis, what's at the target?" The message was brief. "I searched the WISE infrared catalog for the Lyra coordinate, found something interesting. See attached." Park opened the attachment. It was an infrared image, deep and grainy, showing the faint glow of stars and dust. In the center, marked with a red circle, was a faint infrared source, too dim to be a star, too extended to be a planet. The note beneath the image read, "Excess infrared emission at 12 microns. Could be a debris disk or a protoplanetary system or something else. Follow-up needed." Park stared at the image. The target wasn't empty after all. There was something there, something warm, something emitting infrared light. Something, perhaps, that 3I Atlas was heading toward. She forwarded the image to the research network with a single line. "The destination may not be empty." Then she closed her laptop and looked out the window. Somewhere in the night sky, invisible and impossibly far, 3I Atlas was moving, correcting, aligning, steering itself across the gulf between stars toward a coordinate that might hold something we hadn't seen yet. And if the corrections continued, if the alignment refined, then by the end of the month, the probability of coincidence would drop below 1 in a million. Low enough that coincidence stopped being plausible. Low enough that intention became the simpler explanation. This is not science fiction. This is mid-November 2024. Chapter 11, November 15th. The Ghost Lines Return. The spectrum was perfect, Dr. Henrik Larsson, an observer at the Nordic Optical Telescope on La Palma, had been targeting 3I Atlas for 3 nights, waiting for good seeing and clear skies. On November 15th, conditions aligned. 0.5 arcseconds seeing, no clouds, stable atmosphere. He integrated for 4 hours, building signal from the faint object, now magnitude 20.7 and receding into the darkness. When the reduced spectrum appeared on his screen at 3:22 UTC, all 3 ghost lines were present simultaneously. 312 4 nanometers, 487 9 nanometers, 612 8 nanometers, all 3, together, bright and unmistakable. Larsson immediately checked the wavelength calibration. He'd used thorium-argon lamps, standard references that marked known spectral lines with precision. The calibration was solid, accurate to 0.1 nanometers. The ghost lines were real. He measured their profiles. All three were narrow, Gaussian shapes with widths of approximately 0.8 nanometers. That width corresponded to a velocity dispersion of about 40 kilometers per second, consistent with emission from a warm gas at a temperature of 300 to 400 Kelvin. Not hot, not cold, warm, room temperature. That was strange. Cometary gases were either very cold, frozen ices sublimating at 100–150 Kelvin, or very hot atoms excited by solar UV reaching thousands of Kelvin. There was no natural process that produced bright emission at 300 Kelvin, unless the gas was being heated internally. Larson measured the wavelength ratios, dividing the three wavelengths, 487. 9/312 4 equals 1, 56. 612. 8/312 4 equals 1, 96. The ratios were close to 1, 5, and 2. 0 simple fractions, almost harmonic. Harmonic series appeared in physics when systems oscillated at multiple frequencies, musical instruments, resonant cavities, lasers. They didn't appear in natural thermal emission or fluorescence processes. He pulled up the literature on atomic emission. Spectral lines come from electrons transitioning between energy levels in atoms. The wavelengths are determined by the energy differences, which depend on the atomic structure. For any given element, the possible transitions produce a specific set of wavelengths, a fingerprint. Hydrogen produces lines at 656, 486, and 434 nanometers. Oxygen produces lines at 777, 844, and 926 nanometers. Every element has its own signature. He searched the NIST atomic spectra database, entering the three wavelengths, 312.4, 487.9, 612. 8 nanometers. No matches. No known element produced that combination. He expanded the search, allowing for small shifts due to Doppler effects, ionization states, or molecular bands. Still no matches. The ghost lines were orphans, emission features with no known parent. Larson opened the archive of laboratory spectroscopy. Thousands of molecules had been studied in the lab, their spectra catalogued for comparison with astronomical observations. He searched for molecular bands, for rho vibrational transitions, for anything that could produce emission near the observed wavelengths. Nothing. He contacted colleagues at astrobiology labs, asking if any synthetic compounds, amino acids, peptides, organic polymers, had spectral features near 312, 488, or 613 nanometers. The replies were uncertain. Some organic molecules absorbed light at those wavelengths, but absorption wasn't emission. To emit, the molecules would need to be excited, pumped with energy, and then relax by radiating light. That required a power source. Larson sent the spectrum to Dr. Yuki Tanaka at Subaru, who had detected the magnesium-to-iron anomaly. Tanaka compared the new spectrum with her earlier observations. The ghost lines were stronger now, about twice as bright as they'd been in September, and they were more stable, less variability between observations, less flickering. Whatever was producing them was getting stronger, more organized, more persistent. Tanaka ran a spectral fitting algorithm, trying to model the lines as combinations of known atomic transitions, blends of multiple weak lines that, when added together, might mimic the observed features. The algorithm failed. No combination worked. The lines were too narrow, too bright, too precisely positioned. She called a colleague who specialized in laser spectroscopy. "I need help identifying emission lines," she said, sending the data. "They're coherent, narrow, and unidentified." Her colleague analyzed the spectrum for an hour, then called back. "These look like laser lines," he said. "The narrowness, the stability, the harmonic spacing. It's all consistent with stimulated emission from a resonant cavity. But I don't know what the lasing medium would be. Could it be natural? Technically, yes. Nature produces masers, microwave lasers in molecular clouds. Optical masers are rarer, but they're theoretically possible. You'd need population inversion, more atoms in excited states than in ground states, and you'd need a way to pump energy into the system. But what would pump it? Solar UV maybe, or internal heat, or, he paused, or an external power source. Tanaka thanked him and hung up. She pulled up the photometric data, the rotation ephemeris, the timing of all the anomalies. The ghost lines appeared at rotational phase 0. 73, the same phase where the radio emissions occurred, the same phase where the thermal excess was brightest. One side of the object, one active region. One hemisphere producing radio waves, optical emission, unidentified molecules and magnetic fields, all from the same place, all at the same time. She opened a draft paper titled, Anomalous Optical Emission from 3I Atlas, Evidence for Coherent Processes. She wrote carefully, describing the observations, the line profiles, the lack of identification. In the discussion section, she wrote, the observed emission features exhibit characteristics consistent with stimulated emission rather than thermal or fluorescence processes. The narrowness of the lines suggests coherent sources, possibly analogous to natural optical masers. However, the required pumping mechanism remains unclear. She stopped. She deleted possibly analogous to natural optical masers. She rewrote, the emission characteristics are inconsistent with known natural processes and warrant further investigation. Better, honest, less speculative. She saved the draft and sent it to 3 colleagues for review. 2 responded within a day, both saying the data was solid, the analysis rigorous, the conclusions defensible. The 3rd responded with a single sentence, you know what this looks like, right? Tanaka didn't reply, she knew. It looked like a laser. It looked like organized light, emitted at specific frequencies from a specific region with a precision that nature rarely achieved. It looked engineered, but she wasn't ready to say that. Not in print, not publicly, not until every natural explanation had been exhausted. And so the draft sat in her files unpublished while the object continued receding. On November 17th, an amateur astronomer in Spain captured another spectrum. The ghost lines were there, all 3, bright and stable. On November 19th, a university telescope in Japan detected the lines again. On November 21st, an astronomer in Chile saw them for the 5th time. The pattern was consistent. The lines appeared every time someone looked carefully enough. They were not transient. They were not random. They were a permanent feature of the object's emission, a signature that appeared at phase 0. 73, every 4 hours, as reliably as clockwork. Dr. Larson compiled all the observations into a data table. Dates, wavelengths, intensities, profiles. He sent the table to the research network with a note. Ghost lines confirmed in 5 independent observations. Identification remains unknown. Suggestions welcome. The replies came quickly. Dozens of researchers offered ideas, theories, speculations. None of them worked. None of them explained the wavelengths, the narrowness, the harmonic spacing. The ghost lines remained ghosts, visible, measurable, but without origin. And in the quiet conversations, in the emails not saved, in the thoughts not spoken aloud, a single word kept appearing. Signal. Not noise. Not chaos. Signal. Organized light emitted at chosen frequencies from a source that knew what it was doing. This is not science fiction. This is mid-November 2024. Chapter 12, November 22nd, Biosignatures on Mars, Silence from 3I. The announcement came at 14 EST, broadcast live from NASA headquarters in Washington. Dr. Sarah Mitchell, the principal investigator for the Mars Perseverance rover, stood at the podium and spoke carefully, choosing each word with precision. Today, we are reporting the detection of organic molecules in a rock sample from Jezero crater, with isotope ratios that are difficult to explain through known abiotic processes. The room erupted, cameras flashed. Reporters shouted questions. Mitchell raised her hand for quiet and continued. The sample, designated JEZ-17, was collected from a sedimentary rock layer dated to approximately 3.5 billion years ago, a time when Mars may have had liquid water on its surface. Analysis by the rover's SHERLOC instrument shows the presence of complex organic molecules, including aromatic hydrocarbons and possible amino acid precursors, with carbon isotope ratios enriched in C12 relative to C13. She paused, letting the room absorb the information. On Earth, biological processes preferentially use C12 over C13, producing isotope ratios similar to what we observe in JEZ-17. However, certain abiotic processes, such as Fischer-Tropsch synthesis in hydrothermal systems, can also produce enriched ratios. We cannot yet definitively conclude that these molecules are biological in origin. Another pause. But we can say that this finding is consistent with ancient microbial life, and it warrants further investigation. A sample return mission is essential to confirm these results through more detailed laboratory analysis. The press conference lasted an hour. Scientists explained the chemistry, the isotope measurements, the alternative explanations. The message was clear: maybe life, maybe not, but worth pursuing. By evening, the story dominated every news outlet. NASA finds possible biosignatures on Mars. Ancient Martian life. Rover detects organic molecules. Is this the evidence we've been waiting for? Within 48 hours, Congress announced increased funding for Mars exploration. The Mars Sample Return Mission, delayed for years by budget constraints, was suddenly a top priority. ESA committed additional resources. Private companies offered launch services. The finding, though ambiguous, had captured the public's imagination. The possibility of life beyond Earth, even ancient microbial life, was transformative. It changed the conversation. It changed the priorities. And it changed what people were paying attention to. Meanwhile, 19 AU from Earth, 3I Atlas continued its journey, receding at 43 kilometers per second, rotating every 11.4 hours, emitting radio waves, optical signals, and unidentified molecules. But the headlines had moved on. The grassroots observation network continued their monitoring, photometry every night, spectroscopy when possible, radio observations during the predicted emission windows. The object was still changing. The light curve drift continued 0.3 hours per day, steady and linear. The ghost lines appeared in every high-resolution spectrum. The thermal excess remained detectable in infrared observations, but the institutional focus had shifted. Dr. Marcus Chen at the University of Toronto read the Mars announcement and felt a strange mix of emotions. He was genuinely excited about the Perseverance finding. The possibility of Martian life was profound, worth celebrating, worth pursuing. But he also felt frustration. Mars was still there. It would be there next year, next decade, next century. The rocks weren't going anywhere. Sample return could happen in 2035 or 2040 or whenever the funding materialized. 3I Atlas was leaving. In a few months it would be beyond Jupiter, too faint for spectroscopy, too distant for detailed observation. Whatever it was, whatever secrets it carried, the window for discovery was closing. And the world was looking the other way. He pulled up the observation schedule. The VLA was still offline. JWST's next available slot for 3I Atlas wasn't until December. The major optical telescopes were focused on Mars, on exoplanets, on supernovae, predictable targets with approved programs and allocated time. The small observatory network was still watching, still coordinating. But their instruments were limited. They could track the light curve, detect the brightest spectral lines, measure the position. But they couldn't do deep infrared spectroscopy, couldn't measure the magnetic field, couldn't resolve the structure. They could see that something was happening. They couldn't determine what. Chen opened his email and began drafting a message to NASA's Planetary Science Division. Request for observation time, 3I Atlas. He outlined the anomalies, the trajectory corrections, the radio emissions, the spectral lines, the magnetic field, the light curve changes. He noted that the object was leaving, that the opportunity was finite, that this might be the only chance to characterize an interstellar object while it was still observable. He sent the email and waited. The reply came 3 days later. Thank you for your inquiry. Given the current focus on Mars sample return and the upcoming Europa Clipper mission, we are unable to allocate additional resources to 3I Atlas at this time. We recommend resubmission during the next proposal cycle. Next proposal cycle, 12 months away. By then, the object would be magnitude 24, invisible to all but the most powerful telescopes, and those telescopes would be pointed elsewhere. Chen closed the email and sat in silence. He thought about a phrase someone had written in a group chat. We're better equipped to handle ambiguous biology than ambiguous technology. It was true. The scientific community knew how to study life. The methods were established, the questions well-defined, the path forward clear. You looked for organic molecules, for isotope ratios, for metabolic byproducts. You built hypotheses, tested predictions, followed protocols. But technology, artificial objects from other civilizations, there were no protocols, no established methods, no consensus on what to look for or how to interpret it. And so when faced with something that didn't fit the biological paradigm, the community defaulted to skepticism. It was safer. It was more comfortable. It avoided the uncomfortable implications of intelligence beyond Earth. Chen pulled up the trajectory alignment data that Jin Park had sent, the Lyra coordinate, the infrared source, the slow, deliberate correction steering the object toward a destination. He thought about the Mars finding, isotope ratios that might indicate life, organic molecules that might be biological, might be, maybe, possibly. The language of science was always cautious, always hedged, but the level of caution varied. For Mars, might be life was enough to mobilize billions in funding. For 3I Atlas, might be artificial was too speculative to warrant serious attention. Chen understood why. Life fit within the boundaries of known science. Astrobiology was a field, with textbooks and conferences and career paths. SETI existed, but it was marginal, underfunded, viewed with skepticism by much of the astronomy community. Finding microbial fossils on Mars would be the discovery of the century. Finding an interstellar probe would be, what? A challenge to everything, a disruption, a question no one knew how to answer, and so the institutions looked away. But the object was still there, still moving, still emitting signals that a graduate student in New Zealand could detect with a 50-year-old telescope, still waiting for someone to decide that it was worth the effort to understand. On November 25th, Dr. Amelia Cross at SCI received a message from a colleague. Did you see the Lyra coordinate analysis, the infrared source? Cross hadn't. She pulled up the data and spent an hour reading through the trajectory reports, the alignment hypothesis, the WISE infrared detection. Then she opened the JWST observing schedule and checked for available time. There was a gap, 4 hours on December 8th. Not enough for a full spectroscopic survey, but enough to point the telescope at the Lyra coordinate and see if the infrared source was real. She submitted a director's discretionary time proposal, a mechanism for rapid response observations of transient or time-sensitive targets. The proposal was brief. Characterization of infrared source in potential trajectory path of 3I Atlas. The proposal was reviewed, approved, scheduled. On December 8th, JWST would observe the destination. And perhaps for the first time they'd learn not just where 3I Atlas had been, but where it was going. This is not science fiction. This is late November 2024. Chapter 13, November 28th. The core temperature paradox. The reprocessed data arrived on Thanksgiving Day. Dr. Raj Patel, an infrared spectroscopist at Caltech, had been working through the holiday, reanalyzing JWST's thermal observations of 3I Atlas with improved calibration algorithms. The original processing had been quick, optimized for fast results. The reprocessing was careful, systematic, squeezing every photon of information from the data. When the final thermal spectrum appeared on his screen, he called his supervisor. "You need to see this," he said. The surface temperature matched predictions, 220 Kelvin at 17 AU from the sun, consistent with solar heating and radiative equilibrium. That was expected. That was normal. But there was an excess in the long wavelength infrared, between 20 and 30 microns. A subtle brightening, about 15 Kelvin above the expected equilibrium temperature. 15 Kelvin didn't sound like much, but it was persistent across every observation. It was stable over weeks, and it implied internal heat. Patel calculated the power required to maintain that excess. The object's surface area was approximately 300 square kilometers, assuming a sphere 10 kilometers in diameter. To raise the temperature by 15 Kelvin across that area required about 50 kilowatts of continuous power. 50 kilowatts, about the output of a small diesel generator, about the power consumption of 10 average American homes, not enormous, but not trivial, and it had been sustained for at least 4 months, from July through November, longer than any transient heat source could maintain. He pulled up the list of potential heating mechanisms. Radioactive decay. Long-lived isotopes like uranium-238 and thorium-232 decay continuously, releasing heat. Earth's interior is kept warm partly by radioactive decay, about 20 terawatts of power, enough to drive plate tectonics and volcanic activity. But Earth is large. It contains trillions of tons of radioactive material, accumulated over 4-5 billion years of planetary formation. 3I Atlas was small. A 10-kilometer object contains maybe 10-15 kilograms of material. To generate 50 kilowatts from radioactive decay, it would need a uranium or thorium concentration of about 1%, 10,000 times higher than typical solar system materials. That was implausible. Uranium and thorium are rare. They're dispersed, diluted, never concentrated naturally in such high abundances. Tidal heating. Gravitational interactions with a companion object can flex an interior, generating frictional heat. Jupiter's moon Io is the most volcanically active body in the solar system, powered entirely by tidal heating from Jupiter's gravity. But 3I Atlas had no companion, no nearby planet, no gravitational partner to flex its interior. It was alone. Residual formation heat. When objects form from colliding dust and ice, the impacts release kinetic energy as heat. Large bodies, planets, moons, can retain that heat for millions of years, slowly radiating it into space. But 3I Atlas was interstellar. It had been wandering the galaxy for hundreds of millions of years, long enough for any formation heat to dissipate. Even large planets cool on timescales of tens of millions of years. A small object like this should have cooled in a fraction of that time. Crystallization heat. Amorphous ice releases energy when it transitions to crystalline states. This process powers occasional outbursts in comets, sudden brightenings when pockets of amorphous ice crystallize and release trapped volatiles. But crystallization is transient. It happens once, explosively, then stops. It doesn't sustain emissions over months. Chemical energy. Reactions between trapped volatiles can release heat. Clathrate decomposition, redox reactions, polymerization, all are exothermic processes that could, in principle, warm an interior. But chemical energy is limited. Once the reactants are consumed, the heat stops, and chemical reservoirs in small objects are tiny, maybe enough for hours or days of heating, not months. Patel stared at the list. Every natural explanation struggled. The heat flux was small, 50 kilowatts, but it was continuous, sustained, unexplained. He opened a thermodynamic model and calculated how long different heat sources could maintain the observed temperature. Radioactive decay, indefinitely but only if uranium concentrations were absurdly high. Tidal heating, indefinitely but only if a companion existed. Residual heat, days to months at most. Chemical energy, hours to days. None of them fit. He ran a different calculation. If the heat source was internal and localized, a warm region deep within the object, how large would it need to be? Assuming the object had a thermal conductivity similar to ice, a 50 kilowatt heat source could maintain a localized hotspot about 1 kilometer across, buried beneath several kilometers of insulating material. A hot spot, a core, something warm, stable, and hidden. Patel pulled up the spectroscopic data. The 4-6 micron emission feature, still unidentified, appeared to come from the same rotational phase where the thermal excess was brightest. That suggested the emission region and the heat source were co-located. Same place, same time. He thought about power sources, about systems that could generate kilowatts continuously for months in the cold vacuum of space. Solar panels. But 3I Atlas's sunlit side was cold, and the thermal excess was on the night side. Batteries. But no battery could store enough energy to sustain 50 kilowatts for 4 months. You'd need thousands of tons of lithium-ion cells, radioactive thermoelectric generators. NASA used them on deep space probes, Voyager, Cassini, Curiosity. They worked by converting the heat from plutonium-238 decay into electricity. Voyager's RTGs produced about 470 watts when launched, decaying slowly over decades. To generate 50 kilowatts, you'd need about 100 Voyager-class RTGs. That required tons of plutonium-238, one of the rarest and most expensive materials in existence. Implausible for a natural object, plausible for a spacecraft. Patel didn't write that in his notes. He drafted a report, Thermal Analysis of 3I Atlas, Evidence for Internal Heat Source. The abstract summarized the findings: 15 Kelvin excess, 50 kilowatts power, sustained over 4 months. The discussion explored natural mechanisms and concluded that none were fully satisfactory. The final paragraph read, "The observed thermal excess suggests an internal energy source not accounted for in current models. Further observations, particularly high-resolution infrared imaging, are needed to constrain the size and location of the heating region." He sent the draft to his supervisor and to the JWST science team. The replies were cautious. The data was solid. The analysis was rigorous, but the implications were uncomfortable. One colleague wrote, "If the heat source is real and sustained, we need to seriously consider unconventional explanations." Another wrote, "Let's not get ahead of the data. There might be a natural process we haven't thought of yet." A third wrote, "Raj, you know what this looks like. Be careful how you present it." Patel knew. It looked like a power source, a reactor, something generating energy continuously, efficiently, with no fuel visible from the outside. He thought about the phrase that kept appearing in private conversations: active system. Not passive, not inert, active. A system that required power to function. A system that had been operating for months, maybe longer. A system that was still running. On November 30th, a journalist contacted Patel, asking for comment on the thermal findings. The journalist had read the draft report, leaked, somehow, from the internal review process. "Is it possible," the journalist asked, "that the object has some kind of power plant?" Patel chose his words carefully. "The thermal excess requires an explanation. We're exploring all possibilities, including artificial sources. Including sources we may not have fully characterized yet." The journalist pressed, "But you can't rule out that it's artificial." Patel paused. In science, we rarely rule things out completely. We assess probabilities. Right now, the data is consistent with several hypotheses, and we're working to narrow them down. What would it take to prove it's artificial? Direct observation, high-resolution imaging, spectroscopy that identifies manufactured materials, or a signal, something unambiguous, something that couldn't be natural. The interview ended. The article was published the next day. Interstellar object shows unexplained heat. Could it be powered? The research team scrambled to clarify. Press releases emphasized the ambiguity, the need for caution, the possibility of natural explanations. But the public conversation had shifted again. First, organic molecules, then ghost lines, now internal heat. Each anomaly alone was plausible. Each one sat inside the boundary of natural, but together they formed a pattern, a cumulative improbability. A stacked series of unlikely events that, when multiplied, approached astronomical odds. And in the quiet conversations, in the private emails, in the thoughts not spoken aloud, a question began to form. What if the simplest explanation wasn't natural? What if the reason everything seemed designed was because it was? This is not science fiction. This is late November 2024. Chapter 14, December 5th. What the core chooses to reveal. By early December, 3I Atlas was 2.5 astronomical units from Earth. Magnitude 21. 3 accessible only to the largest telescopes with long exposures, and even then, barely. The object continued its trajectory toward the Lyra coordinate, confirmed now by 6 additional astrometric observations. The alignment had refined. What had been a 5-degree uncertainty in November was now 2 degrees. The probability of coincidence had dropped below 1 in 10,000. The radio emissions had not repeated. November 12th came and went. The predicted window for the next 1612 or 1665 MHz signal, but fast, Arecibo's successor in China, and the reopened VLA all reported null detections. Either the emissions had stopped, or they were now too faint to detect, or they had shifted to different frequencies. The ghost lines persisted. Every high-resolution spectrum showed them. 312, 4 nm, 400.